So basically, yeah, I'm going to give a brief introduction into the sort of measurement technique. Um, I'm, I work for LIGO, so this is going to be fairly LIGO-centric discussion, but the principles that we're discussing here apply to Virgo and KAGRA. There are some details that are a little bit different about how their interferometers are configured and designed, but on the whole, it's very similar. But if you have questions about the differences at the end of my talk, please feel free to ask. So I I assume, I'm not quite sure what the level of everybody is at here, but I'll just kind of give a very brief introduction to, you know, gravitational waves and sort of the detection principle. So, everybody, I assume, is familiar with Einstein's general theory of relativity that um, tells uh, how, makes the relationship between the curvature of space-time and its mass energy content, and how that curvature affects the motion of masses in the space-time. A very interesting consequence of the general theory of relativity that Einstein recognized almost immediately, published a paper on it in 2016, was that the theory supported waves of gravitation. I think probably everybody knows this because that's why we're here. Um, and the waves have a kind of an interesting dynamics, which is that they're transverse waves and they produce a strain in space-time. And I'll emphasize this because we're going to come back to what is strain in a minute. But strain is basically the change in length divided by the length. So if you have, a meter that is changing by, 1 millimeter, then that's a strain of 100. Um, and so, or sorry, 1/100, because you have the delta L, which is 1 millimeter divided by 100 millimeters as the over the length. So for a wave traveling in the z direction, it has this pattern where it stretches space in one perpendicular axis and contracts it in the other, and then in the next cycle, half cycle of the wave, it does the opposite, and that's kind of what you can see in this wave tube as the wave would be traveling through the axis of this tube, and this is how the tube would be deformed as the wave is passing through. Um, okay, and people know probably about the history of GR, a history of gravitational waves. This is a very important result, which really, kind of got the field going, was this, essentially, confirmation of the existence of gravitational waves due to the observation of this binary pulsar, which the Hulse-Taylor pulsar, which led to the Nobel Prize in 1993. And you can see on the right the change in the orbital period over time as they did this observation over 30 years, and the prediction from general relativity due to the emission of gravitational waves, and they just perfect confirmation. I think this is a really um, powerful experimental result here. It's such a clear indication of the validity of GR. Um, so then, before this result was published, though, there was kind of a pathbreaker named Joseph Weber, who thought he should be able to detect gravitational waves using resonant mass detectors. And so this is a picture of what one of his detectors looked like. It's this giant bar of aluminum that was meant to ring when a gravitational wave passed by. And you can see he's playing with the transducers that are, around the the cylinder that are going to pick, the design idea is that they'll pick up the motion, the vibrational motion of the bar. Um, he actually thought he made an observation of gravitational waves, but it was never confirmed. Um, so there was a little bit of a dark ages in gravitational wave research after Weber did his work in the 60s. But then starting in the 70s, we had two groups of people at Caltech and MIT that started to get interested in potentially looking for gravitational waves with interferometers, which is what we'll get to now. So this is the principle of a Michelson interferometer, where you have a light source, nowadays a laser light source, that shoots a beam at a beam splitter. The beam splits at the beam splitter and goes down these two perpendicular arms, hits these mirrors at the end, comes back, recombines at the beam splitter, where you then get an interference pattern of the light going on the two arms. And if the arm lengths are set such that there is perfect destructive interference of the light coming from the two arms, then you get no light going to the output. But if the length is slightly adjusted so that the interference pattern moves to constructive interference, then you get light. And so this is a, very powerful instrument. It was used it was invented by Michelson back in the 1800s and was used for early evidence for general relativity, and it's been an incredibly powerful tool ever since. But it particularly is interesting for gravitational wave measurement, because you can see here again is that ring cross section of the gravitational wave passing through space. And you can imagine that if you put a Michelson interferometer in the middle of this, path of the wave, then the mirrors will move with the distorted space-time caused by the wave, and the particular dynamics of the wave are very applicable to the to how a Michelson interferometer works. And you can see that if you put, as the wave passes through, it's going to move these end masses of the Michelson interferometer in such a way that could potentially be detected by a Michelson interferometer. And you would, as the wave passes, you go through these cycles of interference and non-interference of the light leaking out to the detector. So the trick here, though, of course, is that in order to see this effect in the Michelson interferometer, the mirrors have to move by about a wavelength of light, or about half a wavelength of light, which is quite small, but gravitational, or depending on what wavelength you're using, but if you're using a optical wavelength laser or something in the near visible, then that motion that you're looking for is roughly nanometer scale motion, 10 to the minus 9 meters. So, but the trick is, are the gravitational waves actually going to cause a motion of 10 to the 9 meters? So let's, kind of dig into that a little bit. So these two groups at Caltech and MIT started to produce prototype interferometers to see how much they could increase the sensitivity of them to try to make them sensitive enough to detect gravitational waves. And this 1.5 meter prototype at MIT is not around anymore, but the Caltech 40 meter prototype is actually still in active use as an R&D lab. And so that's an actually relatively recent picture of the Caltech 40 meter prototype interferometer there on the right. Okay, so you have this basic interferometer configuration for a Michelson interferometer with the lasers, the beam splitter, the two in mirrors, and the detector. So after many years, this interferometer got a lot more complicated to try to um, increase the sensitivity. So let's kind of briefly go through some of the improvements here. So one thing, the entire interferometer is put into a vacuum system with all of the air sucked out of it so that there's no motion of the the mirrors can't be perturbed by moving air, or the laser beam can't be diffracted by air currents. Um, the mirrors themselves are hung on suspension systems from multi-stage seismic isolation platforms to try to isolate them from the motion of the ground. Um, the laser power is increased as high as you can make it. Instead of just having the laser beam going from the beam splitter to the in mirror, we put in these resonant cavities that build up the power in the arms and kind of have the effect of making it that like the laser is bouncing multiple times in the arm, so that amplifies the effect of the arm motion. We have these thermal compensation systems that counteract the thermal heating of the mirrors due to the high-powered lasers. Um, an important thing is that we try to increase the length of the arms as long as we can. So remember, we're detecting strain, right? The gravitational wave produces a strain, but we're actually detecting the delta L, right? We're detecting the change in the length of the relative length of the two arms. That's what produces the signal in the interferometer. But you want to convert that to strain, so you need to multiply times L or divide by L, which is the length of the arms. So if you want to have um, uh, the strain that you're trying to measure, and the delta L that you're capable of measuring, you can, increase the arms very, very long to get the L very big. And then that has the effect of, producing a larger delta L for any given strain passing through the detector. Um, and then more recently, we've added these quantum squeezers to the interferometers to try to lower the quantum noise. And that's a very fascinating subject in and of itself about how we can manipulate the quantum state of the interferometer. It's one of the coolest kind of tech things that we've done recently to improve these instruments. I won't get into the details of these things, but anyway, there's lots of information out there about all of these ways that we've improved the instrument. But anyway, that eventually led, after all this R&D to try to figure out how to improve the sensitivity. That led to the creation of the LIGO projects, um, where we got funding from the National Science Foundation for MIT and Caltech to join together and build these very long baseline um, Michelson interferometers. And so you can see the Hanford detector on the left in Eastern Washington, and the Livingston detector in Louisiana. And yeah, I should have put more info in this slide, particular about the Virgo detector in Italy, near Pisa, Italy, which is also, again, a long baseline Michelson interferometer, and the KAGRA detector in Japan, near Toyama on the west coast of Japan, which is again a interferometer, same configuration, but it's actually buried inside a mountain into big tubes that are carved out of the inside of a mountain. Like I said, those detectors have um, slightly different, ways of doing all of these tricks that we're doing to try to improve the sensitivity of these detectors, but the principle is the same. And so, for LIGO, here's kind of roughly where they are on the map of the United States. About 3,000 kilometers apart, 10 millisecond light travel time separation. Um, I'll just take a moment to, I don't know, there's a lot of stuff going on. I'm not going to try to get into any political stuff, but we are entirely funded. The LIGO laboratory is entirely funded by the National Science Foundation. And I assume a lot of people here are maybe funded by the NSF, and there's a lot of turmoil in the NSF right now. So I just want to express our deep gratitude for the NSF for funding us and over the lifetime of this project. And I really hope that we continue to appreciate what we're doing here and that the NSF will continue to fund these efforts. But anyway, I'll leave it there. The This is a picture of the central building at Hanford, where you can see basically these very large vacuum enclosures that the entire interferometer is inside of. And so I don't know if you guys can see my mouse moving around, but these big chambers here are hold these multi-stage seismic isolation systems from which the test masses, the mirrored test masses that the laser beams bounce off of, are hung from these multi-stage seismic isolation platforms. These blue, these horizontal blue beams here are the external supports for that seismic isolation system that's inside the vacuum. And you can see under this yellow catwalk here, you can see a person for scale. So this whole thing is really big. And there's a lot of stuff going on in here. This kind of pink thing in the background is a clean room that we put around these chambers when we need to open them up to work on what's inside of them. Yeah, anyway, there's a lot going on. So this is a cross section of the seismic isolation platform, and it's 7 stages of seismic isolation. We've kind of got one external one. We've got 2 stages in this, active seismic isolation platform here, and then we've got 4 stages of isolation in the suspension that hangs the mirror. And where that 7 is, that is the ultimate mass, the test mass itself that the laser is bouncing off of. And this 7 stages of seismic isolation, it's like 7 pendula. So you get, just a massive amount of attenuation of the ground noise. So this is a really critical part of how all of these detectors work, because the ground is moving so much, it would completely swamp out any signal we would be able to detect. So we really have to do a lot of seismic isolation to attenuate that ground motion so that it doesn't get to the test mass. Here's a picture of one of these seismic isolation platforms being assembled outside of the vacuum. That thing gets picked up and plopped into the chambers. Here's a diagram of the suspension system. These bottom 2 cylinders, they look like they look like they're both mirrors, but the laser beam is only bouncing off of the bottom one, and the top one is identical. It's actually made of the exact same material. They're both made of fused silica in LIGO. And the reason that they're identical is because the fibers that hang the bottom test mass from the top one are also fused silica. So and they're welded to the sides of the fused silica cylinders to make this whole structure, in some sense, monolithic. So you have a fused silica cylinder on the top with silica fibers welded to the bottom one, and that's to help the thermal noise. So every time you have a boundary between two different materials, that's a place where you can introduce a lot of loss into the system, which can produce a lot of thermal noise. And so by having the two stages at the bottom be monolithic, all fully silica, then you can reduce some of the thermal noise that would come from those boundaries. Um, and thermal noise is also a really big component of what we have to deal with, and I'll talk about that in just a second. Here's a picture of that same assembly installed inside the tubes, inside one of those big chambers. Here's a picture inside the laser enclosure. So this is our light source. And you can see that that big box on the backside of the table with the red tubes in it. That's our main laser amplifier that takes this 1 micron laser light and amplifies it up to hundreds of watts of power. 100 watts, 100, 200 watts doesn't seem like that much when you think about like a 60-watt light bulb in your house. But this is, laser, all of that light from the light bulb is going in all different directions. This is all focused into a very tiny point, and that is a very powerful beam that laser beam would absolutely burn a hole through your hand if you stuck your hand in the middle of it. So it's very, we have to take a lot of precautions. This is an ultra clean room here so that there's no dust that lands on the mirrors, because we have to keep everything incredibly clean, partially because we use these high-powered lasers. And if a little bit of dust lands on the mirror and it gets hit by this very high-powered laser, it like instantly vaporizes and can leave little pock marks in the mirror that can affect how well affect the optics and affect our sensitivity. So we have to keep everything very, very clean. And this is actually a very old picture of the readout chamber before we installed the quantum squeezing injection system that is used to decrease the quantum noise. So this is an old image, but you can kind of see what it looks like in the readout chamber. And this is just a picture that I really like. This is at the end test mass. This is at the end of one of the arms, and this is um, what they call the transmon assembly. So you can see in the back the test mass suspension assembly, and that dark hole behind the person in the bunny suit there is the long arm that goes down to the central vertex. And then this assembly kind of in the foreground of the image takes the little bit of light that leaks through the test mass. That test mass is meant to be, almost fully reflective, and it reflect almost all the light back towards the vertex, but a little bit of the light leaks through, and we use that for diagnostic purposes. And so you can see what that assembly is there. And that green spot on that mirror in that assembly is actually a green laser beam that we shoot back into the arm from the backside of the test mass for doing alignment and control stuff. And then finally, we have this big digital control system where all of the sensors, we have light leaking out in all sorts of places in the interferometer, and we use all that for diagnostics and for control of all of the suspension systems. We have all these feedback control systems that detect the motion of all the mirrors and then feedback to control them. All the seismic isolation systems are actively controlled. This is all done with a real-time control system, digital control system, and all sorts of automation systems that live on top of that to help us uh, keep the interferometer locked and also get it back to its most sensitive state after we lose lock. I won't talk about exactly what locking means, but it's part of the way that we control. The interferometer is kind of naturally unstable. It doesn't stay in its most sensitive place without this feedback control system. And that because the feedback control system is so sensitive, if an earthquake passes by and moves it too much, then it can go outside of its dynamic range and become uncontrolled, and then we have to calm everything down and bring it back to its fully controlled state, which takes a while. Um, Okay, so fundamentally, LIGO is a transducer of space-time strain into electrical signals. It's basically a microphone of space-time. And this is kind of our most important um, measurement that we do to, evaluate the sensitivity of the instrument is to look at the, the noise that we're listening to in the instrument. So in the absence of gravitational waves, we take the strain signal that comes out of these, we have the detectors with the light being modulated because of the motion of the arms. We turn that into an electrical signal that, we analyze. But the main thing is that that's an electrical signal that is basically in the frequency range of interest in that electrical signal is in the audio frequency range from roughly 10 hertz up to about 5 kilohertz. And so what we need to do is to and in the absence of gravitational waves, it's just kind of a noise. It just sort of sounds like white noise with kind of some tones in it that come from various things like the vibrations of the suspension fibers and all that kind of stuff. But it's basically just a noise. And you know, to understand how well we can detect gravitational waves, that's a function of the signal to noise level. So how loud is a signal going to be in the instrument compared to what the noise level is in the instrument? So the instrumentalists are very interested in understanding the noise in the instrument. And so what we have here is called a noise budget. So this is a very important tool for the instrumentalists, where the bold black curve on the top, that is the that's the the strain or displacement noise, the noise power spectral density. Actually, this is the amplitude spectral density, so it's the square root of the power spectral density. The black curve is the measured noise spectrum. And this is actually a little bit of an old plot. This is from before the third science run. We're just in the middle of our fourth science run now, and our sensitivity is even lower than this, but the same, it's not that much different from what you see here. And in the gray in the background, you can see the old spectrum from earlier eras of the detector, so you can kind of get a little sense of how things have improved. So back when Jonah and I were graduate students doing our thesis research, was during S6 in iLIGO, and you can see in the light gray in the back, hopefully you guys can see this back here, that was what the strain sensitivity looked like back in S6. And so you can see we've improved a lot since then. And there was a lot of improvements made to the instrument between the initial LIGO detectors and the advanced LIGO detectors that gave us a bunch of improvement, which was key to our being able to detect gravitational waves. But I want to just talk for just a second about these dashed curves at the bottom, because that's the important part of the noise budget here. So these colored curves are the fundamental noises coming from the instrument itself. And These are our estimates of what these fundamental noises should be given the instruments in the configuration they were, at least at the time of this plot around the time of '03. Or I think maybe these are the actual design, since the designed, the design budget, which is, what we expected those fundamental noises to be for the initial design of advanced LIGO. Um, but I'm going to talk about the three main ones where we have in green is the seismic noise. So that's this green curve, dashed curve on the left. And that is the residual motion of the mirrors that has leaked through our seismic isolation platform. So the ground moves, is moving at like, micrometers, just kind of ambiently. And, this is, you can see the displacement on the right axis over here at like 10 to the minus 18 meters. So we've attenuated that ground motion by, something like, you know, 10 orders of magnitude more than that, 12 orders of magnitude, the ground motion. So the seismic isolation is a hugely important thing. Then the orange curve, the flat orange line, that is the thermal noise, mostly due to thermal fluctuations in the coatings of the mirrors. That is the thermal noise that is the most dominant one. There's thermal noise in various places in the suspension fibers and the bulk of the mirrors. But the thermal noise in the coatings of the mirrors is the one that affects our sensitivity the most. And that's literally just, the molecules in the coating of the mirror vibrating around are causing a noise. So you can kind of get a sense of the sensitivity here. But how small of a motion we can detect with this interferometer. And then the blue dashed curve is the quantum noise. So that's the noise from the quantum nature of light. Okay, so the fact that light is actually made up of photons, and there's kind of two parts to the quantum noise, is that one is that the photons actually hit the mirrors, with kind of Poissonian statistics. So they actually bang on the mirrors and cause the mirror to move around very slightly. That's called radiation pressure noise, or quantum radiation pressure noise. And then also the quantum nature of light, the photon nature of light, also causes a noise at the detector, because as the light interferes and you've got photons of light hitting the detector at different times. That's another kind of quantum noise. So you add up all of those noises, and then you get the black dashed curve. And so that's what we expect should be the noise spectrum of the instrument. But you can see there's a gap between the black dashed curve and the solid black curve, which is what we measure. And so that gap is the thing that is, those are some kinds of technical noises, some of which we may understand, or some of which we don't understand, that are limiting us from reaching our full design sensitivity. And this is what the scientists at the observatories are spending all of their time doing, basically, is trying to understand that gap and to try to understand the things that are contributing to that gap and eliminating them, so that we can reach the ultimate design sensitivity of the instrument. And these, if you look up in the legend, these numbers on the right side of the legend, for where it says for the LIGO design is something like 200 megaparsecs. So that 200 megaparsecs is the distance to a canonical binary neutron star in spiral source that we should be able to detect with a strain spectrum of that level. So the A-LIGO design sensitivity has a binary neutron star range of about 200 megaparsecs. And then where we were before '03 was at about 100 megaparsecs. So that black curve is about 100 megaparsecs. We're better than that now. We're about up to 150 megaparsecs now. So we've gotten a little bit better. We still haven't reached our full design sensitivity yet, but we keep working on it. Um, so just to emphasize kind of how amazing this is with these very sophisticated Michelson interferometers, at the minima of this curve here, that corresponds to a displacement sensitivity of 2 times 10 to the minus 20 meters. So I've given a lot of talks about this kind of stuff, and it never ceases to amaze me how small this number is. 10 to the minus 20 meters is just insanely small. I mean, that's smaller than the size of a proton. And this is a graphic I always like to show just because it emphasizes this is basically a hydrogen atom with an electron zooming into the proton, and then we're on the edge of the proton, effectively 10 to the minus 17 meters, and this is what we're measuring. This is a graphic from our first detection when our sensitivity was 10 to the minus 18 meters. So 2 orders of magnitude, um, you know, smaller than what it is, bigger than what it is now. And so that's just an incredibly small number. And it's amazing that these instruments can detect motions that are this small, like subatomic, subnuclear motions. These things are really a technological marvel for sure. And so then the last thing I'll talk about is the strain. So, what we measure is an electrical impulse. That impulse is, directly related to the motion of the mirrors. So what we need to do is calibrate that electrical signal into actual meters of motion of the mirrors, and we turn that into strain by just dividing by the absolute length of the arms. So the calibration procedure from turning the raw electrical signal into strain is actually fairly complicated because we need to have a whole model of how the interferometer works, what its dynamics are in order to do that. And it's mostly a function of this digital feedback control system that we use. So in the upper left here, you can see this cartoon schematic of our digital control system where you have the sensing block here is everything that detects the light signal, all of the electronics that amplify that signal and convert it into and digitize it. Then we have all the digital control system that processes all of those signals, and then that produces a digital control system that then goes to digital to analog converters to go and push on the mirrors. And that's all of that stuff is handled in that actuation block. And then we have going into that plus on the left is the actual delta L motion of the mirrors that comes from, gravitational waves, presumably, plus the signal we're pushing on the mirrors to counteract any motion. And so you can see kind of how we unwrap all of this by having a model of the sensing, what we call the sensing function, which is all of the components of the sensing part of that chain, and a model of the actuation. And we can pick off these signals, and with our model of those components, we can produce our estimate of the motion of the mirrors. And to kind of get a sense of the complication of that is this diagram at the bottom we call the subway map, which is basically every component in there that is affecting the measurement that we're making that we need to take into account in our modeling of the instrument in order to produce the calibration. So basically, once we have that model, we have a computer process that can process the data as it's coming in and do the calculation based on our model to produce the strain estimate. Um, that is probably, I think I'm probably at time or a little bit over. I have a bunch of slides about our first detection, which probably you guys are all familiar with. 170817, which is our first, binary neutron star detection back in 2017, which was uh, just an absolutely amazing discovery and led to one of the coolest papers that we wrote with the astronomy community on the multi-messenger observation of this binary neutron star merger. I'm sure a lot of you are aware of this, but let me emphasize that this paper, titled Multi-Messenger Observations of a Binary Neutron Star Merger, is a really good paper. It's very well written. It talks about the physics of binary neutron stars, all the different kinds of signals that they can emit. This was really a landmark. This was almost, I mean, obviously, our first detection of gravitational waves was truly momentous, but this was really a marvel of the entire field of astronomy to make this multi-messenger observation of the binary neutron star merger. And I highly recommend that people read this paper because it's a really excellent paper. And it was a lot of hard work to produce that paper. Um, and then here's just kind of a chart of all of the observations we have today, up to date from black holes and neutron stars. And there you can follow this link that's at the bottom here to get a kind of an interactive version of this where you can mouse over all of these things and get and see what the nature of those signals was. But I'm sure other speakers are going to talk about all of that, so I'll leave that to them. So thank you very much, and I'll happily take any questions.